Okay, so let's start. Today we start with a new topic, which is metal semiconductor contacts. And as we were discussing in last couple of lectures, we've looked at basic properties of semiconductors, and we are now ready to look at some important semiconductor devices here. And let's start with a metal semiconductor contact, which acts as a device in itself. Device in the sense that some of you may have heard of Schottky barrier diodes. So metal semiconductor contacts, using them, we can make Schottky barrier diodes which have rectifying characteristics. Metal semiconductor contacts are also important that whichever device you take, whether it's your PN junction diode or it's your bipolar transistor or it's your MOSFET or whichever device that you take, remember what you have to do is the device may be made up of N-type, P-type semiconductors, but eventually you have to connect it to the external world, and you connect it by using wires. And so you have to make a contact to your semiconductor device using a metal, and then this metal is then connected to a battery or whatever else it is. So if you have to connect your semiconductor device to the external world, and you do that through metal semiconductor contacts. So they are a part of every semiconductor device. Okay, so it's basically then this particular contact in these cases, in PN junction diodes, bipolar transistors, and MOSFETs, a contact actually serves as an interface through which the semiconductor device interacts with this environment. Now, obviously, you are interested. Let's say if I have an N-type semiconductor and I'm using it as a resistor, I'm interested in the N-type semiconductor, right? My properties of the device should be determined by N-type semiconductor. The contact has only been made so that I can apply a voltage here and I can extract a current. And therefore, the contact should not affect the properties of my device. In this case, the properties of my device should be determined by N-type. Similarly, if I make a PN junction, the properties of my device should be determined by the PN junction and not by the contact that I make. In those cases, what I have to do is these metal semiconductor contacts that you see here, I have to make them so good that the voltage drops across them are very, very small. Okay, so how do we describe contacts in such cases here? There is a concept of contact resistivity. Okay, so whatever device you have, and this is a metal semiconductor contact. Blue we'll use it to denote metals. So there's a metal semiconductor contact here. There's a metal semiconductor contact here. And the property of the contact, where the contact is being made to simply allow voltages and currents to be applied to your device, we can describe the properties of this particular contact using a concept called contact resistivity. So remember, nothing is ideal. In an ideal case, what you would want is that the metal and the semiconductor contact that you form, it just allows voltages to be applied and currents to be extracted without any voltage drop. Right? So all the voltage that you apply from your battery, it just goes to your device. Right? So that's what you would want ideally. As I said, you want properties of your device to be determined by the device itself. You don't want the contacts to have an effect on your device here. So in an ideal case, you would want any resistance associated with this contact to be 0 here and 0 here. But in real life, it's not really 0. And therefore, we have the concept of contact resistivity, which is defined as rho C as or 1 over rho C as del J by del V here. J is what? The current density flowing through the contact. V is the voltage drop across the contact here. Okay. Now, the reason why I've defined it in terms of J is that we want it to be determined by the property of the metal semiconductor contact and not the area. All right. If I had taken I, then I would have gotten resistance, and resistance there would have been an area term. And then it's not it depends on size. Otherwise, in this case, it's simply dependent on the property of the contact here. So this is a very important parameter here. A contact will have a certain amount of contact resistivity here. Normally, what we would like this contact to be, we know that it will have resistance. We would like this to be ohmic. Ohmic in the sense that it follows an Ohm's law, and therefore it can be characterized by a simple resistor here. And we would like this resistor to be as small as possible here. So this is the specific contact resistivity. As you can see here, its units are ohm centimeter square. The actual contact resistance would be, in any device, would be equal to contact resistivity divided by area. If you make a large area, then as you might expect, if you make a large area, the contact resistance will go down. If you have a small area, the contact resistance will be high here. Okay, so that's the important concept of contact resistivity and contact resistance here. So let's look at what kind of a number, when I'm making a device, what kind of a number do I want from this particular one? How large or small should this value be here? So to do that, let's look at an example. So we take a PN junction diode. PN junction diode, which is shown over here. There's a P region and there's an N region here. We formed a metal semiconductor contact at the top. We formed a metal semiconductor contact at the top. What I want to know is, this value that you see here, what kind of a value of rho C is good? And if, so to get an assessment of that. So what we have done is, we have taken contact resistivities of several values here. 10 per minus 3. Is that a good value? 10 per minus 5. 10 per minus 6. So we want to calculate the contact resistance due to a series of contact resistivity values here. And we have taken a typical dimension of the PN junction, let's say 10 micron by 10 micron here. 10 micron is the length here, and the width perpendicular to this plane here, the width is also 10 micron here. Okay? Yes?
So, contact resistivity, is it also encompassing the effects of the contact potential?
No, so in this case, this is a model. Or what we are saying is that the contact offers a resistance. That's all. We're not talking about right now. We'll come to that, the contact potential and all of that. So right now, the model that we have is that it offers a resistance. That's it. So when I apply, see, at equilibrium, there may be some drop. But when I apply a voltage, current will pass and a additional drop will develop here. So we're talking about that additional drop.
So this is the
additional drop, yes. Okay. So what we want to know is this, what happens when the contact resistivities are of this value, and how much is the voltage dropped across the contact also. We assume a typical current in a PN junction diode of 1 milliampere. Okay. So it's very simple to calculate the contact resistance. RC will be equal to contact resistivity divided by area. So that's the important equation here. So all that we have to do is put a value of 10 per minus 3 divided by area. Put value of 10 per minus 5 divided by area, and so we can easily calculate here. So let me show a table here. So table shows us the following. When the contact resistivity is 10 per minus 3, area, as you can easily calculate here, contact resistance turns out to be 1 kilo ohm. 1 kilo ohm, I have 1 milliamperes flowing through my PN junction. So the voltage drop across the contact itself is 1 volt. I'll explain what this factor is. 1 volt drop here. Obviously, it's telling you is 10 per minus 3 is a very high contact resistivity, right? If I put 10 per minus 5, I have a contact resistance of, it becomes 100 times smaller. It becomes 10 ohm. The voltage drop across, I'm only talking about the voltage drop across one contact. And similarly, there'll be a voltage drop across the other contact also. Okay, so right now I'm only taking one contact here. 10 per minus 5 gives you 10 millivolt here, drop here. 10 per minus 6 gives you 1 millivolt here. So what kind of a contact resistivity am I looking for? When you make a device and you have to make a metal semiconductor contact, what kind of a contact resistivity do I want? 10 per minus 6 or smaller, or even smaller, right? Now, what is this modification factor? Remember, PN junction diode, current goes as exponentially with voltage here. So you have applied, let's say 1 volt or 2 volts, or what, you've applied a certain voltage to your PN junction diode. Some drop will occur across the contact, right? And you were expecting that the entire voltage will go to your PN junction diode and it will result in a certain current. But some drop will occur across the contact here. As a result, the current would be smaller. How much will it be smaller? Exponent roughly minus the drop across the contact divided by kT. Just to get an idea of how is the current affected. Okay. So if you have a 1 volt drop across the contact, obviously, it's a huge factor here. But even a 10 millivolt, note that it will cause a current to drop by 0.68. So 68% drop. This is the modification factor. So the current would be 68% of whatever is the normal current. If you have 1 millivolt, the current would be 96% of the ideal case here. Okay, so you can see here that I'm looking for, in this case, in a PN junction diode, I'm looking for a contact resistivity of around 10 power minus 6 or smaller. Okay, so that's the kind of a number. So I just wanted to, through the simple example, illustrate to you what kind of a number are we looking for here. Okay, so 10 power minus 6 or even smaller contact resistivity is something that one is aiming for here. Larger than that, then it will result in significant drops and will cause modification in the device characteristics. Okay, so what we are looking for then is very clear, that if I have a certain current flowing through my device, the current multiplied by the contact resistance, total contact resistance, should be much, much smaller than applied voltage here, right? We want the entire applied voltage to go into the device here, not get dropped across the contact here. Now I can do the following. I can write current as J into A, current density multiplied by the area of the device, and RC we can write as contact resistivity divided by area. Areas cancel each other, and so what I get is J into rho C must be much, much smaller than V applied here. What this is telling you is the following, that what is really important in contact resistance is the current density here. And the problem of voltage drop across contact resistance becomes more severe as you make the current density higher. See, you can operate the device. I have a certain area of the device. I can operate it at 1 milliampere. Maybe I can operate it at 0.1 milliampere. Maybe I can operate it 10 milliamperes. Okay. The higher the current density in the device, the more the issue of contact resistivity, contact drops come into picture here. So the issue is, why do you want to make current density very high? Why do you want current density to be high? What is the reason? One reason is obvious.
More compact circuits.
More compact circuits in the sense that, let's say you made a device and say a bipolar transistor, you want to bias it at 1 milliampere, right? Now 1 milliampere, you can bias it at 1 milliamperes. If you have a smaller transistor, what happens to current density? Goes high. But what is the advantage of smaller transistor? You use smaller silicon area, it becomes cheaper. That's the first thing that happens here. The smaller the device, the smaller the silicon area that you use, and the cheaper it gets here. So your interest is in making things smaller. The other thing is, if you're making a large integrated circuit, the smaller you make it, the more you can pack. So in a given area, the more, density of circuits increases here. The other one is, yes, you can, we'll just see, you can change the switching speed of the device, also depends on area. So for a variety of reasons, you want to make your circuits compact, you want to make them cheaper using smaller area, you want to increase the switching speed of the device. All of these you get often by making current density large. And as you make current density large, then you can see here these problems, they become more severe. Okay, this J into rho C becomes more severe here. In a very simple way, some of you may be wondering how switching speed is related to J. So let me show it to you in a very simple way here. In many of the semiconductor devices, you find that the delay is often a resistance and a capacitance. Okay, so delay is like an RC. As I said, this is a very generic, very simple way of showing how delay depends on that. So delay is often an RC, R into C. R is voltage by current. Capacitance, is some kind of a epsilon by D multiplied by area. Charges are separated by a certain distance and there's a certain area involved. So a simple model for capacitance is here. I can write it as J into A. Note that areas cancel each other. And what do you get? Tau is inversely proportional to J, often. So as you increase the current density, you're able to, in many cases, you're able to reduce the delay here. So that's why, and this is very simple. You may have a term here which is a constant. So after a while, as you increase J, tau falls and then becomes a constant. Okay, so this is simplistic, but what it is illustrating is that as you push current density higher, the delay drops here. So that's another reason why we want to operate a device at higher current density. And you can see then, if we go back, that my contact resistivity problem drops become more severe as I make the current density higher here. Okay, so this is an important equation which tells us the importance here. Okay, often what we have is, if you go back and look at this picture here, in this case, what we are saying is that, we have made a connection here and we have made a connection here. The current is flowing how? The current is flowing vertically. right? It is starting from here and going from one contact to the next contact here, vertically flowing down. Many of the semiconductor devices are not like this. They are of this kind here. The devices that we make are planar. One contact is at the top here, and the other contact is also at the top. In these cases, now note, it's not that the current is starting from here and flowing down. The current will start down and then flow here and then flow up here. So look at the flow of the current here, the path. Okay, this is the space between the two contacts is my real device here. That's the portion I'm interested in. This is just this, and this is just to, as I said, is an interface. I have to apply a voltage, I have to extract current. So it's just there to allow voltages to be applied and currents to be extracted here. So I'm not really, so any drop that occurs associated with this region here, and any drop that occurs associated with this region here, that's a drop that I'm not interested in. I want these drops to be small here. So in this case, any drop associated with this region here is, the whole thing is what I will call as contact resistance. And anything that is associated with this whole region here, I will call it the drop associated with my contact. Now you can see here, the contact resistance is not only associated with, this metal semiconductor junction here, but as the carriers come across this, they encounter a resistance, but they have to flow laterally also. And as they flow laterally, they encounter this N-type semiconductor, so they'll face a resistance also. So things are more complicated. Now you can see the carriers are starting from here, then flowing here, starting from here, flowing, and all over. It's a distributed current here. And the drop that takes place through this entire region is my contact resistance. Okay, so in this case, now I want to determine what is my contact resistance in this case here. And as you know that if you take a MOSFET is a lateral device. Even if I take a bipolar transistor, you will see that current from the base contact, it flows like this here into the base here. Okay. So in many of these cases, the current flow is of this nature here. So it's vertical, but it's also lateral. It's a combination of them. Okay. So contact resistivity is important, but along with that, the resistance of the N-type is also important. Right? Resistance of the N-type is also important, and together they determine the net contact resistance here. So let's look at that. We build a model called transmission line model here. Let's understand this particular model here. So what are we saying? The current, this I'll focus on one contact. The current, what happens is, it starts from the contact, flows vertically, and then flows laterally. And then starts from here, flows vertically and laterally, starts from here. And then all the different currents that are flowing from here, they all combine together and eventually flow through this here. All right. The current flow may not be so neat. You may be imagining the current may be going like this here. It may not be as neat as that. But this is a model that is often used, transmission line model, which sort of captures that there is a contribution to the contact resistance coming from the contact resistivity, and there is a part which comes about because of the flow through the N-type semiconductor also. So what we are modeling it is in terms of a resistive transmission line here. Okay, so there is a vertical resistance that you see here, and then there is a horizontal resistance here, and all these resistances are per unit length because we are talking about a distributed model. It's not a lumped model, so we are talking about resistance per unit length here. Okay, so let's look at that here. So you can imagine that so my x-axis is here. We take x equal to 0 here, and then x equal to L. So that gives me the contact length, the total length of the contact here. The width perpendicular to the plane here is W. And so let's look at, so the voltage at any point here, we're taking at Vx. The voltage here is Vx plus delta x, and so on and so forth. Ix is the current flowing here. So you can imagine the current here at this particular point would be 0 because the currents are originating from here. So current at the current here is 0, and then the current here will come and the current here will come. So gradually Ix will build up, starting from a value of 0, and then Ix will build up and reach a maximum value here. And then we'll enter your device. Your real device starts from here. Okay. So all these currents are coming in and they're joining together and building up, and finally the full current flows here. Okay. So we would like to find out what is the overall resistance of this particular contact. How would you define? The current is I. So what is the overall resistance? How would you define that? Can I say the voltage at this point is V at x equal to 0 divided by I will give you the right? Agreed? Because the voltage here is 0, and whatever is the voltage drop here, the difference between the voltage here and the voltage here, which is V0, divided by the current flowing. So that will give me the overall resistance of this particular contact here. Okay, so that's how we will calculate. So let's look at now how the equation for Vx here. So we can see here Vx that you see, we can see here Vx plus delta x is larger than Vx by an amount Ix times the horizontal resistance here. Okay. All right. So before that, a few definitions. So what we are saying is this RV that you see here. Note that this is we are making a distributed model here. So we are dividing it into small increments, the whole contact into small increments called delta x here. Okay. So the resistance, the vertical resistance we are talking about only coming about because of the contact resistivity here. So the total resistance will be, as we said, is always rho c, contact resistivity, divided by the area. Area will be W, which is perpendicular to the plane, times delta x here. That's the overall resistance associated with the vertical. Of course, as you can imagine, it flows through the contact, plus it flows through N-type also. Okay, but we are looking at the vertical resistance only as a contact resistivity. We are saying that is the dominant one. And so this is there, and this we're defining it RV by delta x. Okay, so that's the definition of RV. Similarly, RH, the lateral resistance, the resistance of the N-type, as you know, will be equal to rho, resistivity, L by area. So for a small increment here, delta x, width, and T is the thickness of this N-type layer here. Okay, the overall thickness of the N-type layer here. And rho, resistivity divided by the thickness of the N-type layer is what we call as sheet resistance. It has a specific name. Whenever you have a layer and that layer has a certain resistivity, has a certain thickness, the ratio of resistivity and thickness is what we call as sheet resistance. So this becomes RSH delta x by W here, and this we define as RH delta x here. RH is resistance per unit length here. So these are the definitions of RH. We know RH will be equal to R sheet divided by W, and RV will be equal to rho c divided by W here. And what we are saying is we know rho c and we know sheet resistance. These are things that we already know here. All right. And the overall contact resistance will be equal to this voltage minus this voltage here, which is minus V0 divided by I here. So that's the number that we are looking for. We are looking for an expression for this contact resistance RC. All right, so these are the units here. Okay, so let's look at the equation. So we can write here Vx plus delta x here, this minus this voltage here, or Vx plus delta x is equal to Vx plus the voltage drop here, which is Ix. RH delta x is the net resistance of this particular part here. So we can write this equation here, and so we get a differential equation dVx by dx is RH into Ix. Now we can write an equation for I. What we can write is 0 here minus 0 here, 0 minus Vx, sorry here, 0 minus Vx plus delta x divided by RV. So that's the current coming in this branch here. This current plus the current that is coming from here, Ix plus delta x, must be equal to the current here. So we just write a KCL at this particular node here. KCL at this node, there's a current coming in from here, vertical current, there's a current coming in from here. The two currents add up to give me Ix here. And the vertical current is nothing but 0 minus Vx times RV delta x here. Okay, so this gives me another equation, dIx by dx is Vx by RV here. So we get two equations now. So what we do is now we have to, these are coupled together, but the coupling is very simple. So if I take a double derivative, one more derivative here, I will get dIx by dx here, and dIx by dx I get here. So I will get a simple equation in terms of V here. So that's what we'll do. So we get take one more derivative, and you can write here as d square Vx by dx square equal to Vx by, we define a new, you can see here this has the units of length Lt square. We define a new term Lt or K as square root RH by RV. Okay, so it's a second order differential equation whose You can note RH is ohm centimeter and ohm centimeter inverse. This is ohm. So these have the units of length here. Okay, so this has a simple solution: A cos hyperbolic kx here, and B sin hyperbolic kx here. So that's fine. If we take its derivative, dvx by dx here, I will get an expression for ix here, a general expression for ix. So we get vx and ix here. We still don't know what a and b's are, and then we put the boundary condition here. The boundary condition is IL equal to 0. IL was what? Remember, go back here. At this point, IL current is 0. And I0 is what? I. So we put the boundary conditions here. IL equal to 0 and I0 is equal to I. And then, solve it out. And we get Vx is I0, this equation, the simple algebra here. And then we take the ratio of V0 divided by I0 and we get an expression for contact resistance. Okay, contact resistance then depends on RH, which is the lateral resistance, RV, which is the contact resistivity part here, and there is a term called hyperbolic K times L here, so that's the final model that we have here. Okay, so what we have done is we have put in the expressions for RH and we have put in the expressions for RV. So contact resistance is equal to contact resistivity multiplied by sheet resistance, square root of that, divided by W, multiplied by cot hyperbolic L by LT here. LT is square root RC by R sheet here. So note that the overall contact resistance depends not only on the contact resistivity, but depends on the n-type layer here, the sheet resistance of the n-type layer here. So it depends crucially on that. And of course, width is there. And there is this additional term here, cot hyperbolic L by LT here. Okay, so let's look at some simplifications here. Note that very often you would like contact resistance to be small, and therefore what you would want to do is note that this is cot hyperbolic L by LT. So if I increase L, what happens to cot? Decreases. Cot decreases. If I make L very, very large, where does it go? Cot hyperbolic is what? Cos hyperbolic divided by sin hyperbolic. If I make L very, very large, this term goes to 1, becomes unity. Okay, so you would like to make, but you don't have to make it very, very large. All that we are saying is if you make L by LT, LT that you see here, LT is rho C by RSH. If you make L by LT roughly 3 or, of that kind here, this term basically becomes equal to unity, and your contact resistance is simply equal to rho C, contact resistivity here, multiplied by sheet resistance divided by W. Okay, so that's the overall contact resistance here. Of course, you have to make it L larger than LT. LT depends on rho C by RSH. Okay. All right. So let's look at an example here. So consider a contact of size L equal to 1 micron. Okay. Which means this is the size L equal to 1 micron. Width is 10 micron. Width is 10 micron. Rho C is 10 to the power minus 5 centimeters square. And sheet resistance is 10 ohm. Sheet resistance was what? Remember, sheet resistance was resistivity divided by the thickness of the layer. Okay, resistivity of this particular layer divided by the thickness of this particular layer here. So it has units of ohms. All right. The idea is determine the contact resistance. So it's a straightforward application of a formula here. We first of all look at the this transfer length. LT is rho C by RSH. So we find it's 3.16 here. And so my cot hyperbolic is 3.16. Contact size is 1 micron here. And so it's just simply putting in the numbers. Rho C is 10 power minus 5. Sheet resistance is 10 ohms. W is given as 10 micron here. And cot hyperbolic L by LT. So we put in all of that together and we get 103. 103. If the transport had been vertical, see here, what is happening is starting from here and then flowing here, right? But suppose I had the same contact here and the transport had been totally vertical in the sense that this contact had been at the bottom here. What would have been the overall contact resistance? Overall contact resistance would have been what? Rho C divided by the overall area. And that would have been how much? So 10, this will give us how much? that would have been 10 power minus 7. 10 power minus 7. So rho c divided by 10 power minus 7 would have given you 100. This is giving you 103. A little bit higher here. But note, if this sheet resistance I'd made 100, what would have happened to RC? RC would have increased even more, while the vertical resistance would have remained the same. Rho c divided by area would have remained the same. So this resistance here, when you go laterally, like this here, the resistance of this particular part becomes important. Okay. So what should you do when you are making a device? Let's say I'm making a resistor. I'm making a resistor here between these two ends here. Many of the resistors that you will encounter, when you make circuits are lateral resistors here. So when you're making a resistor and you need a low value of resistor, right? A high value of resistor. So how will you get high value of resistor? You'll put low value of doping. So you'll put maybe 10 power 15. When you put a low value of doping, then what will happen to the sheet resistance? Sheet resistance will become high. If sheet resistance becomes high, which means significant drop starts occurring across your contact resistance. So what should you do? What is the strategy then? You want 10 to the power 15 here, but you don't want the resistance to be high. So what should you do? It's a straightforward strategy. You want 10 to the power 15 here to make a resistor, but you don't want the resistance associated with the contact to be high. What should you do? Well, under the contact here, make the resistance large. Make the doping large. See, under the contact here, what you do is you make the region under the contact here heavily doped. Make it N plus. Make the doping 10 to the power 19 or 10 to the power 20. And similarly, under the contact, make the doping 10 to the power 19 or 10 power 20. In the actual device, you keep doping whatever you want. Right? In the actual device, the doping determines the characteristics, so you keep it whatever you want, 10 power 16, 10 power 15 or whatever. But under the contact, make the doping very, very high. Well, you can do that. It's not, this shaded region that you see here is silicon dioxide. It's silicon dioxide. So before you deposit the contact, you can add dopant selectively. You can add dopant selectively in this region here and in this region here. So what it is saying is often you will find that the resistance under the doping under the contact is usually kept very, very high. And for what reason? Well, two reasons here. One is you can obviously see that as you keep the doping very high under the contact, R sheet goes down. Sheet resistance goes down here. It may become 1 ohm or it may become 0.1 ohm. So this resistance goes down and therefore your overall contact resistance becomes small. Later on, as we progress with the lectures, we'll see that this rho c that you see here, this contact resistivity, that also depends on how much doping is there underneath. If you have a very low doping, 10 to the power 15, your contact resistivity will be very high. If you have high doping here under the contact, your contact resistivity also becomes very low. So for both these reasons here, that you want to lower the value of RC, and that you want to lower the sheet resistance, what you end up doing is under the contact you make doping very, very high. All right. Now suppose this is the calculation that you've done. You have a contact of 1 micron by 10 micron here with a contact resistivity of 10 power minus 5, sheet resistance of so much, and you get a resistance of 103. Say 103.31 is too high for you. You want the contact resistance to be reduced to 30 ohms. What should you do? What are your strategies? By the way, contact resistance is an extremely important problem. A lot of effort and time is spent on minimizing contact resistance in MOSFETs and bipolar transistors and all that. When you're designing and fabricating, this is a serious issue. Okay, so 103.31, let's say, is too high for you. You want 30 ohms. How can you reduce the resistance here? What should you do? Starting from the simplest to the most complex. Okay, the simplest, increasing width or something else. You see, width meaning W. What is the price that you have to pay? The overall device becomes larger, and you note that your interest is in this part, right? Your interest is in this part, and this part, let's say you've already designed with a certain length, width, and all doping and all of that. So you don't want to touch that. That part you don't want to touch. A certain width, for example, width of the device has been, determined by whatever, by device properties here. So you don't want to touch this part here. This is the real device here. And real device has a certain width, so I don't want to touch width. So W I don't want to touch. Then, sheet resist, is it the simplest? I'm asking for what you rightly said, make W large. Okay, that's easy to do it. Okay, what is the next easy one to do? Length of the contact, L. Why? Because note that when we put in our numbers here, this part is 31.62 and this part is 3.26. What can I do to this part? How low can I make it? I can make it 1. But 1, right? So I make L larger. So instead of putting 1 micron, I try to make L how much? What kind of an L? So, see, that's why LT is important here. LT is the length. It's a constant for a particular contact, rho C by RSH here, which is 3.16. So how much should I make L? How much should I make? L should be roughly at least 3 times the transfer length, LT. So 3 times LT, which means 3 times here. So maybe I should make it 10 micron. I should make my contact. So it's telling you these are the equations which will provide you guidelines with how to design your device. So once you know these properties here, rho C and RSH, it tells you LT is L by LT right now is 3.26 or LT is 3.16 here. I can see there that this point, this factor, I can reduce it to 1 or very close to 1 here. If I make length larger to roughly 3 times this, so if I make it 10 micron here, that's also something easy to do. For example, from your E210 background that what is the length and width and all that. As a designer, you can prescribe that. So you can tell, make a contact which is 10 micron, which is fine. So it will reduce it to this value here. Length, obviously, in this case also the area increases. Overall device area, you can imagine that 10 micron you're using here, 10 micron you're using here. So overall, this thing increases here. If now after exhausting this particular part here, and you want it further reduced, then the only way to do that is, well, either increase the doping under the contact here. Note that you don't want your device to be changed. So what you do is you modify the doping under the contact. So you try to reduce sheet resistance here, right? Or you try to reduce our rho C here. Rho C depends on what kind of a metal have I used. Maybe aluminum gives me a certain kind of a contact resistivity. If I use tungsten, maybe it gives me different kind of resistivity here. So now try to, look at the metal semiconductor property here and see which one gives you a lower value of rho C here. So this equation sort of tells you how to design. Okay. If you don't know this equation or don't use this equation, you may end up, for example, somebody may not, don't look at this particular equation. Somebody may end up using 100 micron here length. Let's use a large length, right? Let's use a large length and therefore I'll get a small resistance. 100 micron, does it make any sense? You put 100 micron, doesn't make any sense. Unnecessarily you're occupying a large area and, cot remains 1. Okay, so it doesn't matter here. So this equation is extremely important. It tells you what are the factors which affect my overall contact resistance here. Is the resistivity, is the sheet resistance, and is this particular term here, which again depends on the resistivity and the sheet resistance here. These are the factors that you play around in order to get low contact resistance here. Okay. All right. The issue, of course, you should, throughout this course, as much as possible, we'll also try that whichever parameter we talk about, we also say that how can we measure it, right? Because this is an engineering course and, I'm saying rho C is equal to 10 power minus 5, or I have a contact resistance of so much. How do I measure it? When I'm designing a device, I need to measure, right? So how do I measure it? Well, a very simple way of measuring, well, not so simple because you have to make a test structure like this here. So what you do is you make a test structure. Okay, this is a test structure. So you have one contact here, the same N type. You have another contact. These are separated by a distance, let's say D. You have a third contact separated by a distance 2D, another 3D, and so on and so forth. You can make a larger test structure. I'm sure you can see where we are heading. If I make a total, if I measure the resistance between these two, what will it be equal to? 2 RC. Everybody says 2 RC. One contact here, one contact here, and it would depend on the length of the region here. Right? It's a resistor. So I'm calling K some constant multiplied by the length between the two contacts here. So in this case, it will be LS will be equal to D. What will be the resistance between these two? 1 RC here. Note all the contacts are identical. So 2 RC plus K into 2D. So you know that now if I measure R between these two, R between these two, and R between these two, what is happening is this part is remaining constant and this part is increasing. And therefore, all I need to do is measure R as a function of length here, length of the semiconductor between the two contacts here, LS here. So this is for D, this is 2D, this is 3D here. I measure it, I plot it out, and this one gives me 2 RC. Okay, so the intercept on the y-axis gives me twice the contact resistance here, and therefore I know how much is the contact resistance. Okay, and so that's how you measure these properties here. Of course, there is an assumption here, and what is the assumption? That each of the contacts are identical. That you have to make sure. Your fabrication process must be good enough that this contact is exactly same as this contact is exactly same as this. So that of course is there.